In the previous tutorial, we have considered a very simple circuit in which there are no practically that circuit we usually this kind of circuit we don't use it practically. So what could be a practical circuit? So a practical circuit would be a switch with a diode and an inductor and a resistance. Okay. So previously we were discussing about designing a filter. So right now in this circuit which I'm in the circuit number 2, we have a filter inbuilt. Like this is our voltage in which we are interested in. That means we want to control this voltage by switching the control switch. So let me first tell you how this circuit operates. It's very simple. When you turn on the switch, the current flows. When you turn off, the current freewheels. So it is very similar to the previous example of a simple resistance. If you see these voltages VR, and if you see this voltage, I'm calling it as VD, voltage across the diode, they are exactly the same. That is, when the switch is on, the voltage across the diode is VG. When the switch is off, due to freewheeling, the voltage across is 0. So we are still talking about this kind of pulsed signal. Now we are giving it a new name called VD. There is a voltage across the diode. So we have found out the Fourier series for this particular signal, where this is the switching time interval and this is the turn on time. So we have found out that the Fourier series would look something like this. And we have also discussed that we are interested in this particular term. So our objective is to filter out the unnecessary components that are present in the VD signal. So basically we want to pass this voltage through this circuit, which inbuilt acts as a low pass filter. So we want to filter out the zero component, that is the zero frequency component, DC component of this particular signal, which is the average value, that is D into VG. So let us call this voltage as V0 is what we want here, D into VG. And how would my V0 by VD look like? Let's take it into S domain. It is a first order system, right? It's an RL circuit. So it would be S into L by R, that can be written as 1 plus S by omega C. If I draw its bode for frequencies very very small, than omega c, it is just a simple gain. It is just a simple gain, and it starts falling with minus 20 dB per decade at omega c, which is equal to, in our case, r by l. So our main aim here would be, let's take the magnitude of this. What we want and what we don't want, we are clear about it, right? We don't want the higher switching components like omega s, 2 omega s, and so on. So this particular transfer function, if I write it as v naught is equal to vd into, okay, let us write the magnitude of this equation first. We'll try to substitute s is equal to j omega and see what would be the magnitude of this. That is equal to 1 plus j omega into L by R. That is equal to, if I take the magnitude of this complex number, it would be square root of 1 plus omega by omega c square, right? So it can be seen here that magnitude of VO is equal to magnitude of VD into this particular term. Okay. So let's substitute omega s and see and expect what is the relation between omega s and omega c, such that the output voltage will not contain any higher order harmonics. So if I substitute omega s by, if I substitute omega is equal to omega s in this following equation, then I would be getting Vd divided by square root of 1 plus omega s divided by omega c whole square. So what we expect ideally, I would expect this ideally to be 0. Why? Because I don't want any components of switching frequencies in my output voltage. So in order to achieve this, the denominator term must be very high. That means the switching frequency should be far greater than the crossover frequency. So that's how we eliminate the higher order harmonics, and we can design a filter such that this relation can be achievable. Then we have this relation now, ws by w omega s by omega c is far greater than 1. Usually we go with a thumb rule of greater than or equal to 10 in most of the practical applications. So this will ensure us that VO would be approximately equal to the duty ratio into Vg. What if what is the problem if omega s is close to omega c? Let us say this is approximately equal to 1.